Good morning, everybody. As Jesse said, I'm going to talk about rigid body modeling and probably pay a little more attention to this program called SASREF, which most, if not all of you, will at some point need to use it if you're regularly using SAXS. So the amount of high-resolution structural information out in the biological community has increased exponentially over the past decade or so. And there's a very large number of macromolecules for which we know structures. However, what we're also beginning to realize is biological macromolecules do not function in isolation, right? And they usually, in their function, there is involved a very high degree of interaction with other biological macromolecules. And a lot of these involve formation of complexes, functional complexes. So the focus, justifiably, in the community has shifted more towards the study of macromolecular complexes. So these assemblies, the flip side of this is that they're difficult to study. They're not as easy to study the structures of as the individual components of said complexes, right? There are a variety of reasons for that. Some of them are biochemically extremely challenging. They have low shelf lives and structurally transient, potential flexibility, so there is conformational heterogeneity, which Jesse will talk more about in the next talk. And then for one reason or the other, they're very recalcitrant to high-resolution structural determination. So in instances where you have high-resolution structural information available for individual components, models can be built by rigid body assembly of these individual structures based on some sort of low resolution experimental data, structural data. So historically, that was electron microscopy. But the disadvantage with electron microscopy is there is a size limitation, right? They need to be at least a certain size for them to qualify for electron microscopy. So SAXS, on the other hand, has no size limitation, as you have found out over the past 2 days. And then it is also becoming more and more apparent that it's very difficult to call EM low-res technique. It's becoming increasingly difficult to call it a low-res technique. And the logistical ease of SAXS is very difficult to match. EM is logistically pretty complicated, relatively. The other difference between the two is in EM, you go from envelope calculation to domain docking, whereas with SAXS, you can, in fact, fit the structures of the individual components against each other in space, directly against available scattering data. There are several strategies available, and there is a history for the evolution of these strategies. And, started simple. There is a paper by Wall, Gallagher, and Truhala back in 2000, which basically used ellipsoids, very simple shapes, and then rearranged in space to fit the data, and the simple shapes basically representing roughly in size and shape the subunits, and to find the relative, the optimal position, spatial position of these simplified domains in space to fit the SAXS data. Then there are other techniques which involved use of data obtained from other techniques to generate restraints that can be used to screen, for example, thousands of bead models, which then are consistent with the restraints generated from other techniques, analytical ultracentrifugation, for example. This is called constrained fit procedure. This was, I think, first seen in 1999 from the Perkins group. So basic theory. So in ATSAS, this is the software suite that by now you're all familiar with, and there's a set of tools here which use rigid body modeling. So before I embark on what can be done and the basic applications, just a little bit of theory. So I mean, one thing that I must say is these approaches can be used for both X-ray and neutron scattering. So let's assume there's k number of subunits with known structure. So this term here is the scattering amplitude for each subunit in a reference position. And then S is basically 4 pi sine theta by lambda, which is a term you're now very familiar with. So the aim of the modeling is to find the spatial arrangement of the subunits, the scattering from which will best fit the experimental data that you have. Right? So the subunits are moved and rotated as rigid bodies in order to incrementally change the scattering amplitudes. Right? The scattering intensity can be represented by this equation, where this term is partial scattering amplitudes of each rigid body, each individual rigid body, dependent on the scattering amplitude in the reference position and orientation. This can be calculated using Chrysol. Now, this is the program that you have used yesterday, and this can be used to calculate the reference amplitudes of the individual subunits. Now, how do you calculate how well these are fitting? What goes into the basic term for the goodness of fit is the chi-square, which is represented by this equation here, where n is the number of experimental points, c is the scaling factor, and this sigma sj is the experimental error at each given momentum transfer, each given q. And the model is basically minimized to obtain a target function, which in addition to chi-square also has these penalty terms, weighted penalty terms, which can account for a variety of phenomena, right? The interconnectivity of the subunits. The aim is also to avoid absence of overlaps between the subunits, but to maintain connectivity between the subunits, and a variety of other factors, which I will talk about. So before I get to SASREF, there's a couple of, I think, legacy programs which they are still available in the latest versions. These are basically slightly simpler approaches for rigid body modeling for homo and heterodimers. So they're called brute force methods. And the algorithm basically is dependent on a search grid. You will see, if you look at the documentation, you'll see the term Fibonacci grid a lot. It basically defines the sampling space and the number of directions. And what it is also dependent on is the magnitude of the shift vector, right? So you fix one monomer, let's say we're talking about a homodimer, you fix one monomer, and then you shift the other along the z-axis by a certain amount, which, you know, these are called the angular envelope functions, which are also calculated by Chrysol. And there is an offset, which is about 0.3 nanometers, which is basically to ensure that there are no steric clashes, no egregious overlaps between the two domains. Then in the case of symmetric oligomers, appropriate positioning of the monomer and the generated symmetry mates depends on about 6 parameters, right? There's the shift vector, and then there is the rotation angles. The scattering intensity calculations can be accelerated by applying some sort of symmetry operation because, it's a symmetric oligomer. What is important is the magnitude of the shift vector, right? That is, again, dependent on the size of the monomer we're talking about. So that is dependent on the Rg of the monomer and Rg of the entire oligomer. So what can also be used is information obtained from other techniques about distances between specific residues in the oligomer, right? And then the target function to which the minimization occurs, in addition to chi-square, has these other penalty terms which account for inter-residue distances and, again, preventing inter-subunit overlap. So there are these two programs called globsim and DIMFORM, which are both part of the ATSAS suite. But I have never used these because even for these, most people now use SASREF. So SASREF, the way it differs is simulated annealing is performed to move the domains around when you know the domains or subunits, domains of the same large protein or subunits of a multi-component complex are moved around. So simulated annealing is performed and random modifications of the system happen by moving them by certain amounts in translationally and rotating them by fixed angles. So beginning at a high temperature, you can interactively decide what the temperature is and the speed at which it is cooled down. So all this is something you can control. And the correction factors, the penalty, the weighted penalty terms in the target that you're trying to reach, in addition to the chi-square, they account for interconnectivity as usual, absence of overlaps between subunits, and again, you can introduce information about distances between residues and subunits. When I talk about how to run the program, I will show you how to introduce contacts. And then for symmetric particles, you basically perform the simulated annealing on one asymmetric unit and then apply that to all the symmetry mates. So if symmetry is known, then it helps in accelerating the process. So SASREF is when all the parts of the complex are accounted for. There's another program called Bunch, which takes into consideration a scenario where you have the high-resolution structure of several of the components, and there is missing information for either the linkers between the domains, the termini and NC termini, or there's missing information for the whole domains. So the aim is to simultaneously find the best relative orientation for the subunits and the best possible conformation of the flexible linkers. So the gaps are filled using dummy residues, and a loop or protein fragment with unknown structure is substituted by a flexible chain of interconnected residues with the spacing of 0.38 nanometers. As in SASREF, simulated annealing is used for global minimization, and again, the target function has all the usual connectivity overlap, and because you're also building new structure here, you have a penalty to ensure proper bond and dihedral angles in the dummy residue chains. And then the px is introduced to avoid overextension of the dummy residue loops. So one warning, one caveat for this is loop conformation. This is basically an average and a very approximate picture of what it can be to fit the SAXS data. It should therefore not be considered an actual structure. One thing is the approaches for SASREF and bunch are now combined to in this other program called Coral. I've unfortunately not put a slide for it. That's Coral. It stands for complexes and random linkers. So there, it basically uses a library of random chains ranging in length from around 5 to 200 amino acids. And the way that works is it takes the known structures, puts them in random positions, and then if it is able to fit a linker of known length in that orientation that fits the data well, that orientation is accepted. Otherwise, that's rejected, and then it goes on to the next. So that happens iteratively, and then simulated annealing happens to refine that. And that's how the complexes are built in the case of Coral. I'm sorry I didn't put a slide for that, but it essentially combines the features of both SASREF and bunch, along with this library for random coils. So practically, running SASREF is pretty simple if you know a few things about your molecule. One thing that I forgot to mention is you can use scattering data from the whole complex and nothing else. The other alternative is the whole complex and scattering data from truncation mutants that represent the individual components. So you can combine scattering information in this. But the interactive mode is pretty simple. One thing I should mention is there is also a PyMol plugin, so that is even more interactive. I have never used it, but if anyone has experience with it, they're free to chime in and tell us about their experience with it. But there is an interactive mode. There is a PyMol plugin where you can actually look at the changes happening. So all these are pretty obvious inputs. One thing is you can use either the user mode or the expert mode, so you have variable amount of control on each one of these inputs. One thing I highly recommend is going into it with some knowledge of contacts. Because in my experience with SASREF, while the program claims that if this information is not provided, it can run and it'll run with no information, but the results can be wildly inaccurate. And in the absence of previous knowledge, it can actually lead you the wrong way, because all it's trying to do is reach some sort of shape that fits your SAXS data, and that may not have any biochemical relevance. And it is up to the user to provide appropriate amount of information to keep it on the right track. So you can control, like I said, the annealing temperature. Annealing schedule factor controls the speed of the cooling. And then you can also set parameters for when you want to decide that you have reached the optimal solution. So you can either increase the number of annealing steps or decrease them to prevent overfitting. And there's a variety of such inputs there. Most people run with default values, but this is where input from people who have had experience before, like us, comes in. So you should talk to us when you're trying to use any of these programs, and we can guide you through them. So this is an example of 380 kilodalton protein that I've been working on with multiple subunits, and there is some amount of variability in their relative arrangement. And this is at the beginning of the SASREF process, and this is somewhere in the middle. So as you can see, the fit of the theoretical with the experimental data incrementally improves, as does the relative position of the domains against each other. So just to show you an example of the utility of SASREF, this is an example from 2012, and we're actually looking at a very interesting viral protein, and I was particularly I really like this paper because it was one of those rare, purely structural biological papers. You don't see that anymore. It's a very complete structural characterization using a variety of techniques, including SAXS, of this viral protein that belongs to a two-tailed virus, which infects extremophilic archaea. So that's a very exotic biological macromolecule to start with, which intrigued me. And what was very particular about this virus is it's one of the few viruses which is known to grow a shell and tails extracellularly. So usually a virus depends on the host cell and the machinery therein to build itself, but this can actually grow. And this protein called ATV ORF273, the open reading frame 273, was suspected to be one of the proteins that helped in building this tail extracellularly. And what was particularly intriguing about the protein was pH and temperature-dependent oligomerization states. Right? They were purified at between 7 and 8 pHs, and it was shown to be tetrameric using moles data. So unfortunately, this was at a time when SecMol's SAXS instruments were non-existent. So they did moles separately and then SAXS separately on a variety of different conditions. So inline chromatography on a SAXS instrument was also not quite common yet. So all these were batch experiments. And some of the pHs that were involved in crystallization, they failed in SAXS because the protein was aggregating at those pHs, and SAXS was not, batch mode SAXS was not possible. So I think under current circumstances, these experiments would have gone slightly differently. Nevertheless, the discrepancy they saw was under crystallization conditions. They were looking at different kinds of dimers, open and closed conformation dimers, whereas under purification conditions, which was slightly different pH, they were finding that it was a tetramer. And in the crystallization conditions, the dimers, the open and closed conformation dimers, showed a propensity to form fibers, long fibers, which one could suspect is what is leading to the tail formation, right? They could be an important component in the viral tail formation. Nevertheless, with respect to SAXS, they did the ab initio envelope calculation using a variety of symmetries. So they calculated the envelopes using a variety of symmetries. And then they used SASREF to model dimers and tetramers, and based on the chi-squares, they decided it was a tetramer, and then they also found, and they used a variety of symmetry operators even for SASREF, and they found that the best fit is this P22 DAMF model into which the SASREF refined high-resolution structure fit in. There's a very nice way of combining MOLS, SAXS, crystallography, and various modeling approaches available in SAXS to find the structural preference, at least in vitro, for this protein. This is a slightly...
There's a question related to that example, Srinivas, which is, how do you decide to enforce symmetry in DAMF? When do you make that choice?
Well, I mean, in this case, crystallographically, they saw that there was twofold symmetry. But biochemically, they found that it was a tetramer, so it was a homodimer or a homotetramer. So the likelihood of symmetry was high based on their crystallography and the fact that it was a homotetramer. So even if it was a dimer of dimers, the likelihood of symmetry is high. And they used and they did not narrow their choice of symmetry. They just tried everything, and based on which fit best, they decided on which one it actually is. Does that make sense?
Yeah, in the chat they say makes sense. So,
I mean, for example, in this case, this 380 kilodalton protein that I'm working on, there is obviously no symmetry there, given our initial hypotheses. The initial confirmations were pretty asymmetric, so I know there is no symmetry there. But oligomers are there is a high likelihood that there is symmetry. Oligomerization, again, is not a prerequisite for there to be symmetry, but it is the most obvious case. So there is this other example is of a protein called fibrillin. Again, this is a 330 kilodalton protein. It's a multi-domain extracellular matrix protein that polymerizes to form like 57 nanometer periodic microfibrils, and it's basically essential for tissue elasticity. Widely distributed in blood vessels, lung, and skin, acts as a lattice for elastin, I'm sure a protein that you've heard of, deposition during elastic fiber formation. And the mutations of this protein is responsible for something called Marfan syndrome, associated with a variety of cardiovascular, ocular, and skeletal defects. And my daughter, who's an aspiring cellist, tells me this very famous violinist called Paganini, the very famous sufferer of this disease. Anyway, that's a tangent. So using SAXS and MOLS data on 9 recombinant fibrillin fragments. So they had to do this because this is made up of basically repeats of this very common structural motif called the epidermal growth factor motif, and calcium-bound EGF motifs. There's about 47 of them in this protein, and so they basically fragmented it into 9 different fragments, and they looked at the SAXS structures of all of those. Using SAXS and MOLS data on these 9 fragments, the authors defined previously poorly understood shape and topography of this large contiguous arrays of fibrillin 1 domains in physiological conditions. So therefore, bridging the gap between individual domain structure and microfibril organization. So the approach they took is, they did the usual Damin and Gaspar. They did, like Kushal talked about yesterday, 20 Damin steps. So these were pre-DAMIF days. So this was a pretty extensive project because Damin, as Kushal said, is a much slower process than DAMIF. The 20 DAMIFs, then averaging of all the 9 fragments. Compared those shapes to EM populations they found, and they matched fairly well. But what really helped is a combination of SASREF and bunch to model each of these repeat fragments and then overlaying them into the ab initio envelopes. Bunch they had to use to build these polyproline regions for which there was no structural information, and the linkers between these EGF domains were also not very well known, so they used bunch for that. And as you can see, the agreement between SASREF and the ab initio and the EM kind of gives a pretty high degree of confidence in interpreting the structures of these pretty complex proteins. One other thing that this paper actually brings to mind, and I must say, is just as you do 20 different DAMIF or DAMIN steps to make sure that you're getting a unique conformation, even SASREF or any of these simulated annealing programs must be run multiple times to at least check for reproducibility. So because what you're looking at here is they have overlaid, I think, between 5 and 10 different SASREF process results from that, all of which, as you can see, agree with each other. So that, again, also goes into building confidence in what you're seeing. The other thing is when we talk about rigid body modeling of multi-domain proteins with flexible linkers, and the linkers with a variable degree of flexibility, one has to keep in mind the possibility that one spatial arrangement of these multiple domain structure is not enough to account for the SAXS data that you're seeing. So there are programs available like MultiFoxS, which try and generate ensembles of these. So the ensembles are generated based on your input, which is basically a SAXS profile, a PDB file with the entire structure, and a separate file defining which regions of that PDB file can be considered flexible. Based on that, it generates an ensemble of, a given number, about 10,000 is the default, I think. And then it fits either a single conformation or combinations of different conformations with your SAXS data. And then it takes the best fit and tells you which is the most likely explanation for what you're seeing in your scattering data. So one has to, if you are looking at a structure with flexible linkers, one has to consider this as an option and not just pursue a single solution. So with that, I'll stop and invite any questions.
So we are a little bit over time, but I was hoping maybe you could talk just briefly about what kinds of other information you can use to impose these distance constraints, where those come from.
So if you have, one very important distance constraint in SASREF, which I forgot to mention, is if you are modeling a multi-domain protein, a large multi-domain protein, and you have continuous structural information, and if you are splitting the multiple domains into separate PDBs, you have to give a contact file where you say that the C-terminus of domain 1 is 4 angstroms from the N-terminus of the next domain, domain 2. That is very important because otherwise the random movement of the domains will give you something that is completely... So that is one kind of contact information that you have to give. Inter-subunit or intra-chain interactions that are already known either from high-resolution structures or binding studies or mutation studies, biochemical... if you are looking at protein nucleic acid complexes, then if you have mutagenesis studies and electrophoretic mobility shift assays to show which residues are involved in interacting with each other, those are important constraints to use